Hello all, welcome back. We shall specify the boundary condition and set up the case. Right click setup and click edit. It will open CFX preprocessor. The mesh is imported to CFX preprocessor. We can expand this and see the regions. Okay. Next, let us specify the material properties. Double click default domain. We can expand this. We can change the material property to air ideal gas and the reference pressure to 0 atmosphere. In the fluid models, you can specify the heat transfer option to thermal energy. This is sufficient for this simple case. Okay, we can click OK. Next, we shall specify the boundary conditions. We can see the air inlet conditions are 80 degrees Celsius temperature and the mass flow rate is 0.15 kg per second, and the exit pressure is 1 atmosphere and the wall temperature is 60 degrees Celsius. We shall apply these conditions and solve the case. Right click default domain and insert boundary. We can name this as inlet. By default it has chosen the inlet phase. Go to boundary details. We can specify mass flow rate. The mass flow rate is 0.15 kg per second. The flow direction is normal to the boundary. Let the turbulence be of medium intensity, that is 5%. We can specify the total temperature. This is 80 degrees Celsius. The inlet conditions are specified. We can click apply. We shall not change any parameters in these other two tabs. Click OK. Next, we shall specify the outlet condition. Right click default domain, insert boundary, outlet. By default, it has chosen the outlet phase. Go to boundary details. We shall specify the average static pressure as 1 atmosphere. You can click OK. Next, we shall specify the wall boundary conditions. Go to insert boundary and type wall. Click OK. The wall region is chosen. Go to boundary details. Specify heat transfer as temperature. The temperature is 60 degrees Celsius fixed on the wall. Click OK. Now all the boundary conditions are specified. We shall go to solver control and specify the solver settings. Right click and edit solver control. Here we shall see the details of different schemes like advection scheme, turbulence numerics, convergence control, time scale, length scale option and convergence criteria. First we shall see the advection scheme. There are three options here: upwind, high resolution and specified blend factor. We shall see the details about this one by one. The first one is advection scheme. It is the numerical method used to calculate how quantities like momentum, energy, temperature, turbulence, etc. are transported by the flow. It gives a balance between accuracy, stability and the convergence speed. Okay. So there are three types of advection schemes here. We shall see one by one. The first one is upwind. It uses the values from the upstream cell only and the accuracy is first order here. It is very stable but the accuracy is less and it can be used for initial runs and not for the final cases. The next one is high resolution. It blends the first order, that is upwind scheme, and also the second order, that is central difference schemes, in the regions locally wherever necessary. And the accuracy is second order. It is both stable and accurate and it is recommended for common CFD analysis cases. The next one is blend factor. This is a user-defined blend between upwind and higher order. You can specify the blend factor based on which the solver will proportionately choose between upwind and high resolution scheme. The stability and accuracy will be medium, that is in between these two. We shall choose high resolution by default. Next is turbulence numerics. Here there are two options, first order and high resolution. This is also similar to the advection scheme, but it is for turbulent properties. We shall see them one by one. Turbulence numerics refers to the numerical schemes used to solve the turbulence model equations, such as those for turbulent kinetic energy K, specific dissipation rate omega, turbulent dissipation epsilon and the turbulent viscosity mu T. Okay, these are the turbulent model equation terms. These equations are transport equations just like momentum or energy, and they need advection schemes to determine how turbulent quantities are transported across the domain. Similar to the previous case, here the first order uses upstream cell only and accuracy is first order and the stability is good. For the high resolution, it blends between first order and second order, that is upwind and central difference schemes, and the accuracy is second order. It is both stable and accurate. It is recommended for common CFD analysis. Here we shall choose high resolution. Next, for the convergence control, we can specify around 300 to 400 iterations. This is based on the convergence criteria. If the solution is not converged within 400 iterations, we can further increase it to 500 or 1000 iterations based on the necessity. Next, we shall see about time scale and length scale options. Timescale refers to the characteristic time it takes for a fluid disturbance like heat, velocity or pressure change to travel through a significant portion of the domain. Timescale is given by length scale divided by velocity scale. For example, if you are doing a turbomachinery simulation where the rotor rotates at 60 rpm, that is 60 revolutions per minute, then the time scale will be approximately 1 second. That is, it will take 1 second to complete one revolution. So it represents the characteristic time it takes for a fluid disturbance to travel through. Next, in steady state simulations, the solver uses a pseudo transient approach. It controls how aggressively the solution advances for each iteration. If the time scale is too large, then the solver will become unstable. If the time step is too small, then the convergence is slow. This is for steady state simulations. And in transient simulations, the actual time step, that is delta t, will be used. There are two options available in Ansys CFX. The first one is auto timescale and the other one is physical timescale. In auto timescale, the solver computes the timescale automatically using local flow velocity and geometry, and it is default for steady state. But in physical timescale, we can specify the value directly, and it can be used when the auto timescale is unstable or slow. When you use physical timescale, we can specify the timescale factor. So based on this timescale factor, the local timescale is calculated based on this formula, that is local length scale divided by local velocity into timescale factor. So in this case, we shall specify auto timescale. We shall leave it as auto timescale. Next, we can see what is length scale. There are three options here: conservative, aggressive and specified length scale. We shall see one by one. Length scale represents the characteristic geometric dimension used by the solver. It is the representative distance over which significant changes in the flow or field variables occur. For example, if you are solving a pipe flow, then the characteristic length will be the diameter. Next, and if you are solving the boundary layer flow, it will be the boundary layer thickness, which is the characteristic length scale. There are three options available in CFX: conservative, aggressive and specified length scale. If you are using conservative, the solver will use larger length scale, improve stability, but it will result in slower convergence. It is used for initial runs or poorly converging models. If you are using aggressive, it will choose smaller length scale, it will speed up the convergence, but it may risk instability also. It is suitable for non-complex flows. In the third option, you can manually enter the characteristic length. It can be used when the auto estimates are unreliable. For our case, by default, we shall go for conservative option. We shall leave the length scale option as conservative. Next, we shall see about convergence criteria. Here there are two types, that is RMS residual type and max residual type. And we have to set the residual targets. We shall see this one by one. Residuals are a measure of how well the numerical solution satisfies the governing equations like continuity, momentum, turbulence and energy, etc. at each iterations. In simple terms, residuals tell you how much error remains in the solution after each iteration. That is, lower residuals means the solver has converged very well, and if it is higher, the error is more and the solution has not converged properly. There are two types of residuals, RMS residuals and max residuals. RMS residuals measure the average error across all mesh elements, and the default target is 10 power minus 4. But in CFX, we shall try to keep it at 10 power minus 6 and we shall monitor the convergence. Reaching 10 power minus 3 or 10 power minus 4 is sufficient, but it is better if you are able to reach up to 10 power minus 6. The RMS residual formula is given here. It is root mean square of the residuals in all the elements. Here the summation is given and it is residual to the suffix I whole square. This is nothing but root mean square of residuals in all the cells. Okay. Next is max residuals. It measures the largest residual, that is the worst error in any single control volume, that is in any mesh. It is useful for identifying localized problem areas in the mesh, and it can remain high even when RMS is low if any one small region is problematic. If any one mesh is having some error, then the max residuals will be high. In general, we will be using RMS residuals with 10 power minus 6 target criteria. We can change the residual target to 10 power minus 6. Okay. These are all interrupt controls. That is, we can specify any interruption controls. That is, if temperature reaches beyond this much limit or if Mach number reaches beyond certain limit, then the solver will automatically stop the simulation. So you can specify this by adding in interrupt conditions. You can click this, use some logical expression, right click and create some expression to specify these interrupt conditions. At present, we need not give any interrupt conditions. We shall delete this. Okay. Now the solver settings are given. Next, we shall specify the expressions for exit temperature and monitor during the solver control. Go to expressions, right click, insert new expression, exit temperature. Right click, go to variables. In T, you can find out temperature. select temperature and select the region. Right click, physical locators 2D outlet. Click apply. Now the expression is created. Click apply. Go to output control. Go to monitor tab and click monitor objects. Create a new monitor point, that is temperature exit. Right click, expression, and choose this created expression, exit temperature. Both these names should be different. Click OK. Now the case setup is done. Let us go to Solver Manager. Minimize preprocessor, right click solution and click edit. The Solver Manager is open. You can go to run mode and select local parallel. You can create 4 partitions and start the run. The solver has started. We can see the residuals here. It should try to converge below 10 power minus 4 or 10 power minus 6. Okay. Now we shall go to user points and monitor the temperature. Here we can see the exit temperature is coming down because we have given the wall temperature as 60 degrees Celsius. It will be lying in between 80 degree and 60 degrees Celsius. The solver manager is going on. We can pause and resume after a while. We can see after 150 iterations, the residuals has become flat, and when we see the exit temperature, it has reached a converged value. Initially it started with 333 Kelvin and finally it has converged at 345.96 Kelvin. Okay, beyond which the solver will not converge any further. We shall stop it at this point. You can click stop. The solver is complete. You can click OK, minimize this and go to Workbench. You can right click results and click refresh. In the next video, we shall see post processing of results. Thank you.